Hello and welcome to my video lecture on Maxwell's laws. This is meant to be a sort of summary of what we've learned so far in the class, but before I begin, I just wanted to explain some mathematical symbols that'll be coming up so that you're not terribly alarmed by them. The first one is the divergence. So if we take something and we say the divergence of, let's call it A, which would then be a vector. If we say that is equal to, let's say, B, what that means is that if you have B somewhere, you have A radiating out from it in a radial direction, like this. So this is a divergence. Divergence of A equals B means that if you have B, you get A diverging from it. Now, alternatively, we can talk about the curl of A, which is represented by these symbols. And we can say that A equals B, but this time with a vector. And what that means is that if B is a vector pointed this way, you get a curl following the right-hand rule. So A circles around it like this. Right? And so that's why they're named that way, right? The divergence of A equals B means that if there's B, A diverges from it. And the curl of A equals B means that if there's B, A curls around it, and it follows the right-hand rule, so I actually drew these backwards. Yep, that's right. Okay. So now that I've got that out of the way, let's talk about Maxwell's laws. The first one is Gauss's law. The divergence of E is equal to rho over epsilon. Now, rho is a charge density. It's defined by the amount of charge divided by the volume, which means charge Q, volume V. It's a charge density. We can also look at the magnetic Gauss. Divergence of B equals 0. Maxwell-Faraday's law. The curl of E is the change in time of B. And the Maxwell-Ampere law, which says that the curl of B is equal to the mu J. J is a current density, shown here. It's the current divided by the cross-sectional area that current moves through. Plus 1 over c squared dE dt, the changing electric field. And so that's all we got to go through, and we're going to take each one in order and talk about them. So first off, we have Gauss's law. The divergence of an electric field equals the charge density divided by this epsilon term. Epsilon is just a scaling factor. And what that means is what you showed in lab 1. Which is that if you have charges on it, they have electric fields, and those electric fields point out radially, as is sort of shown here, right? So you got an electron, you have radial fields pointing in at it. If you have a proton, you have radial fields pointing out from it. Easy enough. Next step is the magnetic Gauss. Del dot B equals 0. The divergence of B is 0, which just says that can we have a south pole and a north pole separated from each other? No, sir, we cannot. If we could, then we would have magnetic fields diverging from each of them. But as we showed in class, you can't seem to separate them. Scientists have done their best to try and detect magnetic monopoles, which is what these would be called, and they've found none of them. Well, actually, there was one discovery in like 1980, but no one was ever able to verify it, so we think it was a fluke. So what this means is that you don't get separated south and north poles. They're always together, one on the other. Moving right along, we can zip into the Maxwell-Faraday law right here. The curl of E is equal to minus dB dt, the changing magnetic field, which means that if you have a magnet and you throw it with some velocity v to the left here, then you get an electric field curling around it. Again, the electric field follows the right-hand rule. Although here, I guess it wouldn't follow the right-hand rule because there's a minus. Sorry, so it actually curls the other way. I did it backwards again. Then we can skip straight ahead to the Maxwell Ampere law. And the Maxwell Ampere law shows us that the same basic thing, but with charges, right? So if you have a current that's moving to the right, then you get a magnetic field curling around it, following the right-hand rule. If you have a charge with some velocity moving to the right, you get a magnetic field circling around it. There are other ways to get a time-changing electric field than a moving charge, but moving charges are one of the easiest ways to think of it. But the fact that this term merely implies charge is important, right? This means that you have to have an actual physical current, but this could come from just its own propagating electric field, and that's going to be important. So, moving right along, we can take all these terms and we can combine them together. We can take the curl of the magnetic field, substitute in the Maxwell Ampere law for the magnetic field, right? Mu j plus 1 over c squared dE dt. And we can also apply the curl law. This is a vector calculus rule. It's been established by mathematicians. It's accurate, I can assure you. And we can combine in the magnetic Gauss law and the Maxwell-Faraday law, telling us that the divergence of B is 0, so this term is 0, and that the curl of an electric field is a time-changing magnetic field, which means that we can push this curl right here into this parentheses, and we can see the curl of dE dt is the same thing as minus d squared B dt squared, the second order time derivative of the magnetic field. And what that boils down to is you can just do the math out, and what you get is this Laplacian here, del squared, which is a time derivative in all three directions independently. So what this is saying is that your spatial change, the rate of spatial change, the rate of spatial change, is equal to 1 over c squared, the rate of the time change, which means that how our magnetic field changes in space depends on how our magnetic field changes in time. How our electric field changes in space depends on how our electric field changes in time. Another consequence of these equations is that the electric field and the magnetic field in these cases would have to be perpendicular to each other. These are cases where I've assumed that there aren't charges around. So there don't have to be charges or currents for there to be a magnetic field and an electric field. But in the absence of charges and currents, there is an electric field coupled with a magnetic field, and they're perpendicular to each other. And they're moving in a direction perpendicular to both of them. Now, that's hard to visualize, so I've gone and just drawn it out here for you. This is a wave equation, a wave with a velocity c. But I've drawn it out for you. Here, might not be too clear, but this electric field is pointed up and down. This magnetic field is pointed out of the page and into the page. And C, the direction it's moving is to the right. And that is light. An electric field combined with a magnetic field, it can propagate without any charges around or any currents around. It can propagate without anything around. Nothing in that original equation said anything about a body it was moving in. And so it can propagate through space, right? Light reaches the Earth from the sun. It moves through space for a very long distance, a full solar unit, which is a very, very long distance. And it moves very fast. This c, the speed of light, is 2.998 times 10 to the 8 meters per second. And even more so, you can take properties of this wave and use that to define the light that's reaching you. So the wavelength here, the distance between this point and this point, tells you the color of the light. The amplitude of this wave, how high up these things go, tells you how bright the light is. And the speed, of course, is always constant. So those are the only two things that really change. And there you have it. That's what you've shown so far is enough to prove that not only does light exist, but also that light can propagate through space. It moves at a set speed, the speed of light, this c right here, and that it consists of an electric field perpendicular to a magnetic field. And these things have all been proven, and this all works very well. So there you have it in class. Lab 1, you showed that there's a divergent electric field from charges. Up in lab 6, you showed that you get curly magnetic fields around currents. Lab 7, you showed that you get curly electric fields around changing magnetic fields. Lab 6, again, you showed that there aren't magnetic monopoles, so divergence of a magnetic field is going to be equal to 0. And as a result, you get that light exists, and light is an electromagnetic wave, and it propagates through free space. So that's what you've learned in class. Thanks for listening. Stay safe, take care, and have a good day.